For partial derivative, partial u, partial x means that although u may be a function of x, y, z, we take the derivative only with respect to x, with the other variables as constant. The following example shows how to find the force as a function of x if the potential energy function ux is given. Potential energy ux equals minus ax over b squared plus x squared, where a and b are constants. This is a one-dimensional problem. So fx equals minus the derivative of the potential energy u with respect to x equals minus derivative of minus ax over b squared plus x squared with x. It results in two terms. One is a over b squared plus x squared. The another one is minus ax over parentheses b squared plus x squared parentheses squared times 2x equals a times parentheses b squared minus x squared parentheses divided by parentheses b squared plus x squared parentheses square. Let us consider a conservative system in which only conservative forces do work. Energy is transformed from kinetic to potential or vice versa. We must consider a system because potential energy does not exist for an isolated object. This system might be, as the example system, include block A, block B, and the Earth. According to the work energy principle, the net work done on an object is equal to its change in kinetic energy. Since we assume this is a conservative system, the net work done on the system is work done by conservative force. It is equal to minus change in potential energy. Combining the previous two equations, we have delta k equals minus delta u. We rearrange it, and then we have delta k plus delta u equals 0, or the change in kinetic energy plus the change in potential energy equals 0. Here, the subscript f denotes final, and I stands for initial. We define the quantity E equals K plus U, the total mechanical energy of a system. We write in the equation delta K plus delta U equals 0. We have final kinetic energy plus final potential energy equals initial kinetic energy plus initial potential energy, or final mechanical energy equals initial mechanical energy equals constant. This is called the principle of conservation of mechanical energy for conservative force system. If only conservative forces are doing work, the total mechanical energy of a system neither increase nor decrease in any process. It stays constant. The law of conservation of energy gives us an alternative approach to solving problems. Let's take a look at this example. A chain has length L and mass m and was put on a frictionless table at time t equals 0. The chain is stationary, and d is the length hung over the edge. At the moment that the whole chain leaves the table, what is A. the work done by the gravity Wg, and B. the velocity of the chain? First of all, we make an analysis of the forces exerted on the chain. We consider the segment hanging over the table edge and the segment remaining on the top of the table, respectively. The gravitational force G2 is balanced by the normal force Fn. It is the gravitational force G1 that makes the chain fall from the table. And G1 is not a constant force. It changes in the falling process. We set in one-dimensional coordinate this way. The origin is at the table edge, and the positive direction of x-axis is downward. At the end of the chain is at x. The force G1 equals m divided by L, the mass density, times x, the length hanging over the edge, times gravitational constant G, which is 9.8 meters per second square. As the chain falls an infinitesimal distance dx, the annual work dW done by G1 is equal to G1 dx equals m divided by L times Gx dx. At the moment that the whole chain leaves the table, the work Wg equals the element work integral from d to L equals m divided by 2L times G times parentheses L square minus D square parentheses. For problem B, we consider the Earth, the table, and the chain as a system. Only conservative force G1 makes the chain moving. At the initial position, the mechanical energy E1 equals m divided by L times dg times minus 1/2 d, since the center of mass is at the position minus 1/2 d. The kinetic energy is 0 since the velocity of the chain is 0. As the chain leaves the table, the mechanical energy E2 equals 1/2 mv square minus mg 1/2 L, because E1 equals to E2. Solve this equation. We have velocity v equals square root g parentheses L square minus d square parentheses divided by L. We can solve the second problem from another point of view. Applying the work energy principle, we know the change in kinetic energy delta K equals the net work done to the system. In this case, it is equal to Wg. So we have 1/2 mv square equals mg divided by 2L times parenthesis L squared minus D squared parenthesis. Solve this equation, we have velocity v equals square root g parenthesis L squared minus D squared parenthesis divided by L. We neglect friction force in this problem. If the friction coefficient of the table's surface is mu, in natural processes, the mechanical energy does not remain constant but decreases. Frictional forces reduce the total mechanical energy. If work done by a force is dependent on the path, force F dot product with the R integral along a closed path L is not equal to 0. The force F is called non-conservative force. A non-conservative force is also called dissipative force, such as a frictional force. The work done by the frictional force equals the increase in thermal energy. If thermal energy is considered, the total energy is conserved in any process. If only conservative forces do work, mechanical energy conserves. Both kinetic energy and potential energy transfer each other. The total energy of a system can change only by amounts of energy that are transferred to or from the system. For isolated system, if a system is isolated from its environment, then there can be no energy transfers to it or from it. The total energy E of an isolated system cannot change. The roller coaster car rolling on hills is an example that involves non-conservative forces because this situation is subject to frictional forces. From the work energy principle, the net work done on an object is equal to the change in its kinetic energy. The forces that do work on the roller coaster car, in this case, are gravity and friction. So, the net work equals WC, the work done by conservative force gravity, plus WNC, the work done by non-conservative force friction. The work done by conservative force can be written in terms of potential energy. WC equals minus delta U. Hence, delta K plus delta U equals the work done by non-conservative force. Here, WNC is the work done by friction, equals the integral of friction force dot product with the path taken. A crate of mass 180 kg is released that was being held at rest at the top of a 3.7 meter long ramp, inclined 39 degrees to the horizontal. The kinetic friction coefficient μk equals 0.28. A. How fast is the crate moving as it reaches the bottom of the ramp? B. How far will it subsequently slide across the floor? C. Do the answers to them change if we have the mass of the grid. Solution. First, we draw a diagram showing our understanding of the problem. We assume the gravity potential energy at the bottom of the ramp is 0 because the normal force Fn balances the normal component of the grid's weight. The friction force Fk equals mu k times Fn is equal to mu k mg cosine theta. The work done by non-conservative force equals the change in mechanical energy. As the grid reaches the bottom of the ramp, the work done by friction force is mu k mg cosine theta times the length of the ramp d. The minus sign indicates the direction of the friction force is opposite to the displacement. EF is the total mechanical energy at the bottom. It is 1/2 mv squared. The initial total mechanical energy is potential energy at the top. It is mg d sine theta. Solve this equation for V and substitute g d mu k and theta with the data given. We know the velocity is 5.5 meters per second as the grid reaches the bottom of the ramp. At the level floor, the friction force is mu k mg. The work done by this non-conservative force is minus mu k mg times the distance s. The initial velocity is 5.5 meters per second. The final velocity is 0. Solve this equation. We know the grid slides across the floor a distance of 5.4 meters. From the algebraic form of the results, it can be seen that the answers do not change with mass. Newton's law of universal gravitation says that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This force acts along the line joining the two particles. This means that two objects has no attractive force as the distances are as far as infinite. So, we let gravitational potential energy U equals to 0 for R equals infinity. Since the change in potential energy is always defined as the negative of the work done by the conservative force, we have UR minus U infinite equals the minus work integral from infinite to R equals the work integral from R to infinite. Therefore, the gravitational potential energy U equals minus G m divided by R, where the G is the gravitational constant. Please note that as an object approaches the Earth, its potential energy decreases and is always negative. Find the escape velocity v of a satellite of mass m, which is projected into the air from the Earth. me is the mass of the Earth. re is the radius of the Earth. In another word, we are supposed to find the minimum initial speed needed to prevent the satellite from returning to the Earth. We consider the Earth and the satellite as a system. Of course, this is a conservative system. The total mechanical energy is constant. We assume the satellite is launched at the surface of the Earth at speed v1 and eventually goes around the orbit of the height h above the Earth's surface at speed v. As the satellite is launched at the surface of the Earth, the mechanical energy is 1/2 of v1 squared minus g_me m divided by ie. On the orbit, the mechanical energy is 1/2 of v squared minus g_me m divided by re plus h. Solve this equation for v1. We have v1 squared equals to v squared minus 2 times g_me divided by re plus h plus 2 times g_me divided by ie. We apply Newton's second law, F equals to ma, to circular motion. The centripetal acceleration here is v squared over re plus h. The centripetal force is g_me m divided by re plus h squared. So we have v squared equals g_me divided by re plus h. Substitute this equation into equation 1. v1 can be obtained. The lowercase g here is the gravitational constant near the Earth equals 9.8 meters per second squared. v1 equals the square root g re times parentheses 2 minus re over re plus h parentheses. Since re is much larger than h, we have v1 is equal to square root g re. The radius of Earth re is about 6,380 kilometers. Thus, the minimum launching speed for a satellite to orbit the Earth is 7.9 kilometers per second. If the launch speed is high enough, the satellite may escape the attraction of the Earth and go into space. Then h is much larger than the Earth radius re, with final speed v approaching 0. So we have 1/2 of v escape squared minus g_me m divided by re equals 0. Therefore, the speed for escape is square root 2 GIE equals 11.2 km per second.